discussion of networks and anylogic. Okay, so ladies and gentlemen, I'd like you, in case you haven't already, go add a new model. We're going to have to go through this quickly. We're going to have network example. I'm going to call it 858.394 so I can go post it easily. Ladies and gentlemen, you should have watched some videos, so you should be able to tell me some of the steps, many of the steps of this. I'm trying to get you ready for your problem set. So as soon as this finishes creating the model, what do I do next? What do I need to do next? I want this to be an agent-based model, so what do I need to do? Yeah, let's add an agent. Okay, good. And we're going to make it a person. Let's go to the person class and let's give them a depiction. Without prejudice, I'm going to pick once again an oval as I want. It's actually because it's really easy to color. That's the only thing. You can add the pictures of people that are down there in the pictures palette. These sort of things. If you wanted to, you could make yours a lorry, but it's just a little bit more complicated to color them. That's all. Okay, so we've done this. Okay, we want to add a population of people. How do we do it? Okay, main. Good, and we drag it over, and we'll call it a population, and this population will be of size 200. Okay. Population of agents, right? Here, population of agents, yeah, 200. Okay, ladies and gentlemen, that's good. We are going to set these people so that they are laid out in a defined structure. Okay, so we're going to go to main, and in main, we're going to go down to the area which dictates network and layout, and so that's down here under environment for other agents, and we're going to choose it. Oh gosh, this is too small, and I apologize for that. I really need to make this larger. Can you folks see this, or should I make it larger right now? You want to make it larger? Okay. Pardon me while I pause the video. I'll continue here. That's going to lead to funky effects in the video probably, but okay. Okay, so we're going to impose a layout. So we're going to station in a ring, okay? In a ring, geometrically. They're going to be put in a ring. Later we're going to come back and set the network types, which has to do with connectivity, topology. Who's connected to? But right now we're setting layout, the geometry, where people are laid out in space. Okay? Okay, ladies and gentlemen, we should be able to run this model, and you should be able to see people arranged in a ring. Do you see that? Okay. So just to rehearse, we created a person. To that person, we added a blibbit. We went to main, we dragged person in, created a population of size 200. So we had to be population of agents, 200. And we then scrolled down here, and that was in under main. We scrolled down, and we set this to be a ring layout. People okay with that? Okay. Ladies and gentlemen, next, we want to set these people so they are in a network with respect to one another. And we're going to start with a very localized network structure, a structure whereby they'll be connected with others in a ring, with just their neighbors in a ring. How would we do that? What network type would we use? Sorry? Okay, ring lattice. Okay, good. Good. Okay. So now we're going to have people connected, but we want to show that they're connected. So let's go to person, and let's scroll up a bit, and you'll see connections here. So I went to person, and I scrolled up, and I went to connections. And I want to go down to this thing where it says draw line connecting agents, and I want to connect it. Can you folks see better now, the monitor? Okay. So here under person, under connections, do draw line between people. People okay with that? Okay. Okay, so we're going to now run this model. What should we see? So just to rehearse that, to make sure people got everything I did, I was in main. The other thing I did was I applied a ring lattice to the network type in main. Scroll down. In main is just near where we set the layout type. People okay? Okay? If you're having issues, feel free to pull over to your neighbor. I know we're going pretty fast here. Okay, so this is what we see. The network connections are not obvious, but they're hidden behind the people. To make them obvious, ladies and gentlemen, we do have some recourse. So within this connections area, we can actually say draw on top of agents. Okay, that's interesting. Okay, so they're in are they in a ring lattice network? Make sure the network type, in addition to the layout type, should be ring, and then the network type should be ring lattice, and it should be network connections between agents. And go to person, make sure is it also draw lines and draw top. Okay. Okay. Yeah. Try one more. Interesting. Make sure the line color is black. I'd have to look at it otherwise. Yeah. Okay, folks. So this is what we see. Okay. So this is good. We're off to a good start. Let's go now and add some dynamics to this. So we want each person to have a progression. We want to be able to model contagion within this network. And this contagion will spread from person to person. How do we capture that? How can we capture that? With a person can be either susceptible, infected, or recovered. How can we capture that? What's our construct? State chart. Okay, so let's go to person, go down to state chart, and let's drag in a state chart entry. We'll call it infection state chart. Okay. Yeah. Let's draw in a state called susceptible, and let's draw in another state called infective, and a third state called recovered. Okay, recovered, and we're going to set here a parameter called mean time until recovery, and we will set it so that we go from infective to recovered at a rate given by this mean time until recovery. But in what way will it give it? So this is going to be a rate transition associated with recovery. And what do you think the rate would be? If we have a mean time until recovery of, say, 10, what would the rate be? Sorry? 0.1, yeah. So be careful, 1.0 divided by mean time. We actually don't need the 1.0, but it's good to be careful sometimes, because sometimes you'll write just without thinking 1 divided by 3, and it will turn out to be what? It'll compute it as 0 because of integer division. So mean time until recovery. Mean time until recovery will be 10 time units. Okay, 10 time units. Great. We're making some progress here. Now, ladies and gentlemen, what do I need to do to have this be a model of contagion, to have the infection spread? Good. And what sort of connection should that be?
Message.
Should be a message transition. So I'll call it an infection transition. By the way, I'll do show name, so the names of this are more obvious. And I'll do show name here, so the names of these are more obvious. So this will be infection. It'll be a message transition. Okay? It'll be unconditional. In other words, whatever message you get, we don't have to check what it says, we'll just get infected. Okay? If we're susceptible, we'll get infected. If we're not susceptible, that message will fall on stony ground, we won't even notice it, and we won't get infected. Okay, so that's one piece of the equation. That's one side of the coin. But it takes two to tango. What's the other component of it? So if we want infection to be spread, one thing is getting infected. What's the other one? Infecting, transmitting the infection. So there's several ways we can do this in anylogic, but one of the most simple would be to draw a transition from infective into itself. So in this case, the idea is you stay infective, but this thing goes off periodically. So we'll call this exposure, because it's not necessarily transmitting it for sure. If nobody hears it, it won't go. It'll go at a rate, and we're going to drag in a parameter called contact rate. Okay, contact rate, and this contact rate will be a certain number of contacts per day. Okay. And we're going to make it 10 contacts per day. Okay? 10.0. Excuse me, I'll make it 1 contact per day. 1 contact per day. Okay? And here, in this place, for the exposure message, we'll have a rate given by contact rate. What will that contact do? What will that contact do in order to spread it, ladies and gentlemen? It'll send a message. Good. So this transition, when it fires, it has an action associated with it. There's some command, set of commands to undertake, some statements to put in place. So when it happens, when there's this contact, it'll actually do something. And it will, in this case, send a message, right? So this dot send to random neighbor. You're going to send to a random neighbor. Excuse me. I stand corrected. Send to random connected. Neighbor will be in space. We'll get to that. We're going to send a message that says exposed. Now, the particulars of message are not really relevant here. Why aren't they relevant? Because what?
Between quotation marks.
It's the delivery and reception that's important.
Yeah, exactly. So this is the delivery of it. In the reception, just unconditionally, if the person who receives it is susceptible, they go here. They don't even pay attention to the contents of the message. So in this case, it isn't that important. In other cases, it may be quite important. Maybe there's different types of transmission messages. Some are maybe behavioral influences. Some are transmission of one pathogen or another, Hep C, HIV, what have you. in which case it may be very important what you send. And using enums, using option lists that are basically enums that will encode uniquely the name of the message, that can be very useful. But for now, this will be all. Okay? You send a message exposed. Okay, ladies and gentlemen. Okay, we're almost done with the basic mechanics of this. What remains? Sorry? Okay, color remains. That's true. Okay, let's do color. That's a fine thing to prioritize now. I was going to deal with the logical dynamics of it, but okay. So we're going to impose a variable called color. And what type will it be? Yeah, capital C color. And maybe we'll make it initially black. And then when we go to susceptible, we'll make it green. Infective, we'll make it red. Recovered, we'll make it gray. People comfortable with that? Okay, that's an underwhelming response. Okay, color equals green. We're just assigning to the variable in the entry action. When we get to susceptible, we're going to turn it green. When we get to infective, color equals red. When we get to recovered, color equals gray. Okay? Good. Okay. And what's the final component that we have to undertake with this color to actually make it change their color? Okay, well, okay, we're coming to that, and I like how you're looking ahead. But how do we make this color? If we set it as it is now, we have this variable called color, and we assign it in each of the places. Is it going to change color? No. It might as well be called, foobar. It doesn't know what color is. How do we tell it to, okay, change the color accordingly?
Change the fill color.
Okay, yeah, change the fill color associated with this. Okay, fill color needs to be set to depend on color. Okay. So a lot of little mechanisms here. Hopefully this will be really useful for your problem set. I'm trying to apply this, but we're going to have fun looking at some of the consequences of these different types of networks. I'll buy it very quickly. Okay, so we set the fill color here to be color. Great. Okay, shall we run this model? What do you think is going to happen? Anything exciting?
No.
Why not? What's missing?
An initial effect.
Okay, good. Okay, now we have several routes to initial infectives. I'm going to do one that you may consider a little bit of fun. Okay? So, in person, ladies and gentlemen, select the oval. Scroll down to the advanced area and go to the on-click handler. Okay? And on the on-click handler, what we're going to do is get ourselves infected. Okay? If we're clicked on this .infection state chart, yeah, you could just say infection state chart if you want to, .receive message, and we're going to pass it a message. We could also send ourselves a message. We could say this .send such and such, but I'm going to say exposed, okay? So if we're clicked on this .infection state chart .receive message exposed. So if we're clicked on, this thing is clicked on, we're going to send our state chart a message exposed. Does that make sense? We're going to send ourselves. We're going to tell, hey, I got a message exposed. Okay. Yeah, now get infected. So in short, infection is going to be started by what? Click. By click. Okay. Okay. People comfortable with that? Okay, let's run it. Okay, good. So, ladies and gentlemen, click. Okay, what do we see with the ring lattice network in terms of how the infection spreads? Spreads laterally to adjacent neighbors. It actually can peter out very easily. Why? You notice that? actually has trouble really catching on long term. Why is that? This one's going gangbusters, but it eventually stops. Why is that?
Because every person only has 2 connections at most.
Yeah, they actually, in fact, only have 2 particular people whom they're connected. They're having the same number of contacts per unit time as we'll see for other networks, but they're with the same people. And so there are these bottlenecks. And if someone along that bottleneck is recovered, you can't infect them. If they're already infected, you can't infect them. So there's only so far the infection can go easily. It's like, as I said earlier, if you're exposed to the same people day in, day out, you know, if they're already recovered, you're not going to be infecting anyone. Right? Okay. So ladies and gentlemen, how would that compare to the case if we were to have a different sort of network? Where do we go to specify the network? Riddle me this. Main. Yeah. Thanks. Okay. So let's talk about a different sort of network. What other sort of network depends on, is based on ring lattice as part of it? It's it's a small world network. A small world network, ladies and gentlemen, is sort of mostly a ring lattice network. 95% of the connections are with your neighbors, but 5% are with anyone in the population. Okay? Maybe we'll first illustrate, just to be consistent here. Let's first do a random network. I like that suggestion. Let's do a random network. Here, any 2 pair of people, any 2 people are equally likely to be connected. There's no notion, ladies and gentlemen, of locality. There's no notion that if A knows B and A knows C, then C probably knows B.
So how many edges do you have?
So with a random, we'll give it the same number of edges on it. Let's say, actually, let's make this. I'm gonna change things a bit just to make it a little bit more interesting. I'll go back and run that ring lattice with 4 connections per agent, just so you could see what it's like. You don't have to do this, but just so we're sort of being comparable in our treatment of it. This is what happens with 4 connections per agent. It goes a little bit further, but you have some of the same basic issues of geometrical bounding. Actually, it's topological bounding. It can only go so far. So that's 4 people per person. Let's go look now, ladies and gentlemen, at a case where we have a random network where you're connected with 4 people. What do you think this will look like? Just before you run it, what do you think it will look like visually? Yeah, it'll have sort of webs here. Okay, let's start off. What do you think is going to be the difference between what we've seen? Is it going to be bounded? No, it's going to be able to spread very easily across the entire network. Why? Sometimes it will peter out. That one petered out a little bit. Why does it spread? It disseminates. Yeah, you have these global connections. It can leap across the entire network. It doesn't just spread locally. It doesn't just spread to the same basic subset of people. It can leap across and go to very different areas of the network. Think of it as like sparks from a prairie fire. It can spread out and ignite all these different areas around if there's a high wind. So here, ladies and gentlemen, with a random network, which models random mixing between people, you can get huge amounts of spread. Ladies and gentlemen, where have we seen an assumption of random mixing before? That people just kind of bump into each other without structure, without having the same connections they bump into. Yeah, SIR model assumes random mixing. It's assuming that people just bump into each other, that they're not bumping into the same set of people, they're bumping into anyone throughout the population. And you can see there's a really big difference between that and with locality connection. Here it disseminates like wildfire. It goes really, really quickly. Okay, so ladies and gentlemen, now we want to go to a mixture of those two, something that's mostly local, mostly ring lattice, but it's got a small bit of random. And again, I said it's like, suppose 95% of our connections are with our neighbors in a ring lattice sense. They're with our immediate neighbors, with our local connections, with our neighbors. Think about it in the real world. 5% of our connections are with people who knows where across the world. Okay, so what do you think this will look like visually? It seemed unhappy. Pardon me for a second. I took my eye off the ball here. Sorry. I put D. Neighborhood length fraction. Sorry, it should be 0.95. Okay, 0.95. Okay, what will we see visually? Anyone? Well, it looks kind of familiar, right? We have a ring lattice, but then why do we have these kind of webs across it? Anyone? Yeah, those are random long distance connections. Okay, so what's going on here? What is this more like in terms of its dynamics? A ring lattice or a random network? It has much of the characteristics of both, but it actually will lead to dissemination globally, much like a random connection. It's true that structurally, folks, it's mostly a ring lattice network. 95% of it, 95% of those connections are local. But that 5% that's global makes all the difference in terms of the observed behavior. It really disseminates very quickly. With just a small number of global connections, it can move very quickly across the network. Very, very quickly the infection can spread. And it's actually more like a random network in the sense that it disseminates broadly and quickly, despite the fact that 95% of the connections are local. It's that small bit of connections that are global, that tail that wags the dog here, once again. It's that small number of global connections that make all the difference. Okay, ladies and gentlemen, so we can see a dynamics there that's reminiscent of random, even though the structure is mostly ring lattice. Okay, ladies and gentlemen, we're quickly running out of time here. We'll just run two more here. And one, ladies and gentlemen, will be a scale-free network. Okay? Scale-free. I'm going to lower that 10 to 8. Okay? And there's actually a relationship between that and the mean number of connections. Whoa, okay. Sorry, in order to make it representative, in order to make it parsable, I'm gonna see lowering it. Okay, lowered it to 2. That's much more representative. What's going on here? Can anyone parse what's going on? Well, most people actually have relatively fewer connections, but a few people have lots of connections. Where are those people located? Yeah, they're located over here. So with the ring lattice network, if I'm not mistaken, this actually has a mean of about two connections. Be easy enough to calculate. Time is a fleet, and you folks know how to calculate it. Where could you calculate that? You could go to the population, add a statistic. Statistic would compute the average number of connections a person has. Well, maybe I'll just do that now. It'll be a skill that you'll have. Okay, so here we can add a statistic. This will be mean connection count, and this will be an average of some expression over the entire population. The criteria will just always be true. Everyone gets counted, and it will take an average of item, that's the person involved, dot get connections number, boom, there we go. Okay, that's it. Be actually much more instructive yet. Had we time, I'd construct a histogram. Anylogic has this very nice support for histograms, and you could have a histogram data object, fill it in with information on the number of connections. Here we go. And we could click here, mean number of connections per agent, 3.96. Same number of average connections. What do you think will happen if I click on this? Guess who are some of the most early people to get infected, ladies and gentlemen? People in this large number of connections. Why? Why are they among the earliest to get connected? I'm connected with someone, I'm putting this on someone with very few connections, but why are these people getting disproportionately connected early on? Well, it's because they have large number of connections. They're a magnet for infection. They're connected with a lot of people out there. So if there's infection out there circulating somewhere, they're going to tend to get infected before others. And you can go and explore this if you created histograms. If you look at the histograms of the number of connections between those are infected versus those who aren't, you would see disparities there. Those who are infected will tend to have a larger number of connections, for example. I would invite you to play around more with this. Just be aware that we have a large number of network types. Ladies and gentlemen, we're going to break now. I have not shown you all network types. There's actually another one, for example, the distance-based network that's in 2D, and it's not amenable to showing with a ring lattice, but it captures the locality in 2 dimensions, not just in one, connected with people on either side, but in 2 dimensions, where it depends on the geometry where people are laid out. And that's also got very localized dynamics. Thank you very much for your patience. I know we covered a lot today. There's some conceptual material, some theoretic, and some experimental. I hope this will give you a head start on your problem set. And please do take a look at it tonight if possible so we could talk about it on Thursday if questions arise. Thank you very much, folks. Yeah, come on over.
Yes, I have a question here about
You bet.
problem 1. I have my model laid out here, and I don't think
Great.
it's exhibiting the sort of behavior that we want. So I'm just wondering,
Sure.
take a look at it.
Okay.
Maybe point hit to.
Let me just stop this
Sure.
this recording here because we don't need that.